my dad, and he's about to finish this major job you've been working on, which is the James Webb Space Telescope.
Sun shield for this James Webb Space Telescope.
Hey, it's me, Destin. Welcome back to Smarter Every Day. The James Webb Space Telescope is about to launch, and this is a really big deal that people from all over the science community have been waiting on for years. By the time you watch this video, it may have already launched, or it may have been in operation for decades. It doesn't really matter, because today we are going to talk to a very special person, and we're going to learn a lot about the James Webb Space Telescope. The James Webb Space Telescope is too big to fit into any rocket payload fairing, so in order to get it to space, it has to be folded up and launched in this more compact configuration. After launch, it's designed to unfold like origami in what I see as a series of precisely choreographed engineering miracles. Not only do you have to make sure all this stuff works, but it has to happen after the incredibly violent vibration environment of a rocket launch. Projects like the James Webb Space Telescope, or the JWST as it's known, take so long to make and are in operation for so long, it's incredible. You just saw my dad, and I would be fascinated with the James Webb Space Telescope whether or not Dad worked on it or not, but the fact that he did makes it pretty darn special for me, and in an upcoming video, we're going to explore exactly what Dad did on the sun shield, because it's really cool and there's a lot to learn there. But first, I want to learn about what the James Webb Space Telescope is, how it works, all the important things, and we're going to do that by talking to a very special individual. A number of years ago, back in 2017, I had an incredible honor. I was invited to Goddard Space Flight Center, and I had the opportunity to speak with an incredibly important person working on the project, Dr. John Mather. Before we start this conversation, I want to explain its importance to you. If you could pick any human in all of history to explain the James Webb Space Telescope to you, you would pick Dr. John Mather. First of all, he's an astrophysicist and a cosmologist, and he actually won the Nobel Prize for Physics along with George Smoot for his work on the Cosmic Background Explorer satellite. What I'm trying to say is he understands the night sky like no other.
And astronomers have been looking for the center of the expanding universe for a long time, and there is no sign of it. Imagine an infinite universe that is expanding into itself infinitely, without boundary, without a center, without an edge.
The second reason you'd want to listen to Dr. Mather talk about this is because he is the senior project scientist over the James Webb Space Telescope. And what that means is he represents the interest of science to the project managers over the project. And given the fact that he knows all this stuff and the whole project is about science, you can imagine how important that means his perspective is. Not only are we speaking to a brilliant mind who knows many, many things, he's also very kind. For example, when I'm doing the interview, which isn't the best execution of an interview I've ever done, I'm trying to film him in the side room of a little conference center. My camera kept overheating, and he was very patient with me, as I hope you will be too. It's just really, really simple. Like, we're talking about the most complex thing that humans have ever built in a very simple way, and I'll interrupt throughout our little interview here, and we'll have some little simple drawing conversations. It'll be fun. So let's do it. Let's go talk to one of the many brilliant minds working on the James Webb Space Telescope, and let's try to get smarter every day. All right, so this is Dr. John Mather. Am I allowed to say Nobel laureate?
Yes.
All right.
Yes, indeed.
Do you mind talking to me about James Webb for a second?
I'm happy to do that.
Let's go ahead and get comfortable. So what I'm interested in doing, with your permission, is creating a video series about how the James Webb Space Telescope works.
Okay.
And you're the man, correct?
Well, I'm one of the many.
I've heard...
I'm the original senior project scientist.
I've been told that you are the man and that you're very humble and you give credit to everyone.
I'm also proud of what we've done.
Okay.
But yes, it's obviously a team project.
Okay.
It's a huge team project. That's
right.
The special art of it. Here's the telescope, and you can see that it's not like anybody else's telescope. It's not like the little tube that Galileo looked through. It's not like the Hubble Space Telescope. It is way out there in space. It looks more like a solar energy concentrator. And it has this huge hexagonal mirror made out of 18 smaller hexagons to collect the starlight or the galaxy light that comes from over here. Bounces off of that, bounces off a little convex mirror up here and back down into this black area, which is the beginning of the instrument package.
Is that called a Cassegrainian?
These two parts make it a Cassegrain. Mm-hmm. There's a third big mirror that you can't see that makes it called a 3-mirror anastigmat telescope, which is better.
Say that one more time.
3-mirror anastigmat.
I'll have to go look at that.
Yes. It means that it gives a good image over a much larger piece of sky.
Got it.
And so we really care about that because we want a really good image and we have a big camera.
Okay, so I did have to look that up. 3-mirror anastigmat. 3-mirror anastigmat. Basically, it means that light gets bounced off of mirrors 3 times before it gets to the instruments or sensors that are taking the picture. Each of those mirror bounces is for a very specific reason. The big mirror essentially is like a big bucket. It collects all the light as it's traveling through space, and then they focus that down. They wanted as big of a mirror as possible because that means they can get more light, a bigger bucket. So all this light reflects off that big concave mirror and is focused down onto the little secondary mirror in front of it. Think about it. That is so much more light hitting that little mirror than if the little mirror was just looking out into space by itself. All that light then goes deep into the telescope and is bounced off one more mirror, and then it goes to what's called the fine steering mirror. This mirror compensates for the movement of the spacecraft and kind of works like image stabilization, and back here in the back on all these optics, that's where all the astigmatism is taken out of the image. 3-mirror and astigmat, but there's a 4th mirror in there to work like image stabilization. Got it.
The hardest thing for us to build was this giant mirror, because it's made out of 18 pieces, and they all have to be adjusted to the right place after we get upstairs into space. So each of them is made out of beryllium, which is very light and very stiff and holds its shape when it's cold. That was our hardest thing, to learn how to make them ultra light, because each of these hexagons is something you'd be able to lift with your hands if we'd allow you to do it. So they're really thin material and really, really accurate. Behind the telescope mirrors is the instrument package, which has the cameras and spectrometers, and we had to invent some things for that too. We needed much better detectors. The detectors are made of 2 flavors, one called mercury cadmium telluride, and one is called arsenic doped silicon. And the combination of those 2 things give us the sensitivity to the whole wavelength range that we wanted to study.
And that didn't exist before?
Well, they existed, but they weren't good enough. They weren't sensitive enough and they weren't big enough.
Gotcha.
So we really had to push on that. Other things that are obviously difficult is how you're going to make this big thing. So what I'm pointing at here is the sun shield. So it's made out of 5 layers of thin plastic coated with metal.
Kapton?
Kapton. So the sunshine comes up from this side and it's all reflected away. So only a little tiny bit of heat gets through to this side, because we want the telescope to be cold and also very stable.
Basically, the telescope will be flown in such a way that the sun's rays are always hitting the bottom or the instrument side of the sun shield and leaving the mirrors in the shadow. Just like on Earth, when we only see the stars when our side of the planet isn't facing the sun, which we call nighttime, well, with this big sun shield, the Webb can create its own continual night for the telescope. One side of the telescope is always in the dark and the other side is seeing light, which is a really interesting way to do this, because typically you have to do thermal management systems to keep everything at the right temperature. But when you keep the optics cold, you don't have to worry about temperature fluctuations. So you can set it the way it needs to be and you can let it do its thing. This is a fascinating engineering problem, and we'll talk about this more in a future episode.
Things that are more ordinary, we still have to think about. On the warm side of the sun shield is the spacecraft box that contains all the spacecraft electronics, the power supplies, the rocket engines, the fuel tanks, the transmitters and receivers, and the computers. Everything that it takes to run the observatory. It's on this side.
Is that how you also position the spacecraft? Where are the reaction wheels, for example?
We have reaction wheels in here that are used to point the spacecraft in the right direction. And we have rocket jets, which are used for 2 things. One is to maintain the orbit, because it's an unstable orbit. And the other is, once in a while, to unload the reaction wheels, because the reaction wheels collect angular momentum. And where do you get the angular momentum? You get it from sunshine, which pushes on the telescope and isn't totally balanced. So the combination of those 2 things means you have to use fuel. And that's the thing that sets the lifetime of the observatory.
Okay, that was a lot, but we can understand it. Check this out. Reaction wheels are amazing, and I did a whole video on them years ago that goes into depth, but it's basically a way of orienting or pointing the spacecraft without using a rocket, just like cats do. You should probably go back and watch that one too. One way I like to think about reaction wheels is motocross. This video from way back shows it pretty well. So a motocross racer goes flying up into the air, and they're briefly kind of weightless, like a spacecraft, but riders are able to control whether the nose of the bike goes up or down by braking or accelerating. If they accelerate the back wheel, the nose goes up because the reaction torque spins the bike in the opposite direction of the wheel. And if they want to pull the nose down, then they hit the brakes, and all the torque of slowing down the wheel is redirected into the bike and it tilts down. Basically, it's the same idea on a space telescope, but instead of attaching motorcycles to it to turn it in different ways, they have little electric flywheels that are always spinning, and if they accelerate them or decelerate them, the angular momentum is transferred to the telescope and they can spin and point the spacecraft very precisely in all sorts of directions using a combination of reaction wheels oriented in different directions. The other thing that's fascinating about the James Webb Space Telescope is we're trying to keep it oriented in a very specific direction, but we're getting all this pressure from the sun. It's called solar radiation pressure. Basically, as light and radiation from the sun hit the telescope, they actually apply pressure to it, not unlike a sail. It's a really small amount of pressure, like 1,000th of a gram on a square meter of spacecraft. But if you think about it, if you're in 0 G in the vacuum of space, a small force can offset everything, and you have to account for that. It's a really big deal.
So way back in the back of it, where you can't see it in this black section behind the mirror, is a huge box full of instrumentation. And the instruments include cameras and spectrometers to cover the entire wavelength that we can see, which ranges from 0.6 microns, which you can see with your eye, out to 28 microns wavelength, which you definitely cannot.
So he said the spectrum ranges from 0.6 microns to 28 microns. That's a measure of the wavelength of the light they'll be able to detect. This means the telescope will just be able to see the red portion of visible light, but it will look deep into the infrared spectrum. Obviously, there must be some huge advantage to focusing so much on the infrared spectrum, and he's about to talk about that in a little bit.
So we also have spectrometers that spread out the starlight into the rainbow of colors, and to find all the measures of what's going on inside the object. So the first thing you want to know is what's it made out of. So then you look at the what's called spectrum lines. So the spectrum lines come from different chemical elements and molecules. And just as you see when you look at the fireworks on July 4th here, each different color comes from a particular chemical element or molecule.
But it's different though, because you actually have shifting, right?
Yes.
How do you know that you're detecting the correct elements if you're redshifted?
You actually have to detect a pattern. If you only see one line, one spectrum line, you cannot be 100% sure what's making it. So you really need to find two or more if you really want to be sure you're seeing what you think you're seeing. So, but then this accounts for the fact that sometimes the objects coming toward us are going away from us, or participating in the expansion of the universe as a whole, which can change the wavelength rather substantially. A thing that's going away from us has the wavelengths of light that we receive increased. So the fractional increase is called the redshift. So it can go from 0 or even minus if the thing is coming toward us to large numbers. And so far, the farthest thing we've seen with the telescope has a redshift of 11, which means the fractional shift is 11, means the wavelength that we get is 12 times what it was when it started.
Oh, so that's a multiplier that you're talking about.
Multiplier.
Oh, wow.
So if you see, for instance, the Lyman alpha line at 0.12 microns wavelength, by the time we get it, it's at 1.44.
So this is why infrared is so important, because
Yes.
everything is shifted that direction.
Right. So for studying the distant universe where the expansion has stretched out all the wavelengths, you definitely have to have an infrared telescope to study the light that started out as ultraviolet.
So quick question. So if you've seen a shift of 11 times, does that mean that you have a sensor on board that will sense beyond 11 times?
Yes.
Okay.
Yes. So our telescope, well, it depends on what wavelengths you started with.
Right.
But if you started with that particular Lyman alpha line from hydrogen, at a redshift of 11, it's 12 times the original wavelength. There's 1.44 microns.
Got it.
So, but suppose the universe has got things even farther away, so that we see even more expansion since that time. We're set up to see, and we think we might see, objects out to a redshift of 20 or 30.
Are you excited about that?
Yes. Nobody's ever seen them. They are predicted. We are fairly confident of some of those predictions.
Okay, my camera kept overheating, but this is a good time to talk about redshift. You've experienced this in a way with a siren and the Doppler effect. As an ambulance or siren comes towards you, you experience a higher tone, but as it passes you and moves away, that tone gets lower. The sound waves from the siren are compressed against each other as it comes near you, so it appears to your ears as if it's a higher frequency, and the sound waves seem to be expanded as it moves away from you, and your ears perceive it as a lower frequency. The same thing happens with light. So as light from a star that is moving away from us reaches us, the way we see that light is an expanded version of that light. Like the tone from the siren drops, the frequency from the light appears to drop, and it moves from the visible spectrum down into the infrared spectrum. So if we didn't look into the infrared range, we couldn't see light that started out as visible light on things that are moving away from us. This is the red shift. And in a universe that's ever expanding, many of the objects we're looking at and looking for will be moving away from us. So looking in that lower infrared spectrum is super important.
So this is a giant tripod. There's 3 legs. The hinge points here, 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 and to the one, and this leg folds in half. And here's the hinge point. So to get this ready for launch, we pull this one out sideways. So you can pull the mirror up here, and the legs actually fold around behind the observatory.
Wow.
So it just fits.
You had a glimmer in your eye when you said that. That's kind of that's a big deal.
Yeah, it's a big deal. It's one of many things that have to work when you launch. Of course, everything is folded up for launch. Everything has to unfold and do the right thing out there. So, of course, the big question everyone has is, are you sure it's going to work? And the answer is, of course, you can't be sure. But we are doing what we should be doing to make sure. So what do? Well, number one, you have 2 of everything when you possibly can. So you get 2 shots when you need them. You rehearse everything. You practice and practice and practice. And you have grouchy people come to tell you when you're not doing it right. And that's really important because we hate doing it wrong even if we don't like being told.
What are those people? The quality assurance officers?
Those are review panels. We get peer reviews, we get senior engineers that have done something related before and that have a good instinct about these things. They say, no, don't do it like that. Do it some other way.
Right.
And so, but the most important thing is you test and test and test. Because there's no such thing as analyzing anything well enough that you can be sure.
You know, you have destructive tests and non-destructive tests. So how do you perform a test when you only have one test article?
Well, we actually made several test articles. We made a pathfinder for the telescope with the carbon fiber framework, and we put on 2 of the mirrors, or even finally 3.
And my camera overheated again. At this point, I'm starting to get embarrassed, but don't worry about it. This gives us an opportunity as the camera cools off to get distracted by cool things at NASA. This interview took place at NASA's Goddard Space Flight Center in Greenbelt, Maryland, which is where they've been controlling the Hubble Space Telescope for the last several decades. I spoke to the Hubble operations manager and got to see the actual control room. That's a topic for another day, but they do all kinds of awesome stuff here at Goddard. So you're going to make this space telescope and you're going to put it up into space. You don't want the first time it sees a vacuum or near absolute zero on the sensor side. You don't want that to happen for the first time in space, so you got to try to simulate that on Earth. How do you do these incredibly physically challenging things here on 1 atmosphere on the surface of Earth? The answer is a huge thermal vacuum that was built at Goddard back in the 1960s, and it's incredible.
So basically a large vacuum, and they pump liquid nitrogen into it
To make it cold?
make it cold, make it simulate the environment of space.
That's crazy. So this is how you simulate space on the ground.
That's right. This is what it takes.
That's amazing.
I love the legacy look of it, you know?
Yeah, it looks like a boiler, but backwards. Is made to keep pressure out instead of take pressure or contain pressure.
All designed on paper, you know, back in the 60s. You think about it like that, it's all analog.
Okay, so we're on the top floor now. We are walking towards the top of the thermal vacuum chamber. That's cool. So do they actually put James Webb in there?
Some of the components, before the assembly, they would take some of the larger components and put in this one. And then we have a bunch of smaller ones over there. They test everything, all the way down to the nuts and bolts. These are also thermal vacuum chambers, just also, or just smaller scale.
Oh, this is for component level stuff.
Correct.
Gotcha.
Nuts and bolts.
Nuts and bolts.
And smaller assembly parts.
Oh, that's cool. They've got the hydraulic diagram like integrated to the valves. That's pretty neat.
When do you think that was printed, you know?
Oh, wow.
My bad, got a little bit distracted. The next thing they want to test for are the launch forces that happen on the rocket. They have a huge centrifuge at Goddard, and they can place instruments on that and simulate the G-forces that the telescope will see during launch. It's pretty awesome. And then there's the vibrations that'll happen during launch.
Okay, this is the shaker table. So the Ariane is going to shake violently. What you have to do is you have to make sure that the telescope isn't going to break during launch. So here at Goddard Space Center, check it out. It's a really cool area here. This is the way they test that. They'll put the telescope here, they'll mount it in position, and then they'll shake it violently to make sure that nothing falls apart, nothing breaks.
Here's some B-roll footage of them doing that, the vibration testing. You can see the telescope shaking.
Okay, I'm in a really neat spot right now. This is the tent that they moved James Webb around with. It's like a portable clean room. And this is the sound chamber where they're gonna acoustically load the thing.
What they're doing here is simulating the roar of the rockets, which can get up over 140 decibels and can be very destructive. So they've got this big chamber with speakers in it with a massive subwoofer and other speakers to blast it with sound.
That's a subwoofer up top?
This is the largest subwoofer in the country, as far as I know. And so if you really want to drop the bass, this is where you come.
The cool thing about a sound chamber is that the sound is different at different parts in the chamber because you get reflections and echoes off the wall. For example, if I have a sound wave going across and bouncing off the wall, you might get constructive interference, meaning you get a louder sound at different points and you might get a quieter spot. So in order to test that, you can see they have microphones hanging at different points in the chamber. Wow. I'm going to get back behind this because I don't want to interfere with what they're doing. These people are moving this tent by hand, and the way they're doing that is on an air bearing. They've got compressed air pumped to the feet of the tent and a really flat surface floor, and they're able to move the whole thing by hand.
Here's a couple of really cool shots where you can see people moving the entire space telescope by hand within the portable clean room on a cushion of air. Can you imagine what they're thinking? This is so rad.
So my camera's overheating. Is that a problem on the telescope?
The observatory doesn't overheat because it's facing outer space. The whole telescope is protected from the sunshine, from the Earth, and from the moon all the time by this giant sun shield. And we chose the orbit especially so we could do that. The Lagrange point 2 orbit that we choose is actually the only place you can go where the single-sided umbrella that we build can protect the observatory completely from all of those things at the same time.
Lagrange points are special points in space where when you have two orbital bodies interacting with each other, there's these little special spots where things can kind of just balance. They're right in the sweet spot where they're being pulled in two different directions at the same time, and they just kind of hover there. Lagrange points are fascinating. There are 5 Lagrangian points for any combination of two orbital bodies. Since James Webb sensors could be affected by Earthshine and moonshine, L2 of the Earth-Sun system is the optimum place for it to be, and Dr. Mather is about to explain why.
How are you going to communicate with it if it's on the other side of the moon?
It's not. We don't go to that exact spot.
Okay.
And of course the moon orbits as well.
So are you orbiting the Lagrangian point?
We orbit around the Lagrange point. We don't go to it. Number one, it's easier to get there. Number two, the Lagrange point's in the shade. It's actually right behind the Earth. And most of the sunshine is being blocked by the Earth at that spot, so you don't want to go there.
Can you draw that for me on this piece of paper?
Yeah. So sure. Here is the here's the sun over here. Here's the Earth over here, and not to scale, but out here is the Lagrange point, and we are going to be orbiting around the Lagrange point like that.
Just enough to get the sunshine around the Earth?
Yeah, we'll be.
Where's the moon?
The Earth. The moon is a lot closer in. The moon's a lot. My handwriting is not so good today, but the Lagrange point's about 4 times as far from the Earth as the moon is.
Oh, I see.
So we never have a problem with that.
Gotcha. And so I didn't realize that you were choosing to orbit.
Yeah.
I thought the whole point was to. Yeah, I guess.
No, we need the sunshine.
Why?
We don't want to go in the. We need solar power to run the observatory.
Okay, I see.
So we need the sunshine. It also takes more fuel to get to.
Do you not have an RTG on board?
No, we don't. There's no need for it. That's hard to do. So and we need several kilowatts of electricity. So.
Where are the solar panels?
The solar panels are hidden in this picture, but they are obviously going to be on the sun side of the big sun shield. But a few kilowatts is actually small for a giant observatory.
It is.
So that's because what's over here on this side doesn't use anything much.
Gotcha.
Only a little bit of energy to run the detectors.
I know you're excited about what's going to come out of the telescope.
Yes, indeed. Who knows what's out there that we've never guessed at. We have wonderfully exciting things to work on that we know about. The first stars and galaxies, the first black holes, how the galaxies grow, how stars are being born today with planets around them, and even planets around other stars and the outer solar system, where we'll learn something about how solar systems work and maybe even how come the Earth is special or not. The Webb telescope will make beautiful pictures as well. They will be different, of course, because we pick up light at different wavelengths. But those beautiful glowing gas clouds, we'll see them too, just differently. We are, among other things, trying to see through those glowing clouds to see what's inside. So the stars that are being born inside, you can't see them directly right now because that dust and gas is obscuring them. The infrared light that we will pick up can go right around those dust grains and see inside. So our hope is that it'll look different and also beautiful.
So you're saying the infrared light can go through those dust grains?
Yes, infrared light, well, all light bounces off dust particles.
Right.
But the longer the wavelength, the less bounce.
I see.
So the infrared light can go through the clouds. That enables us to see things.
Oh, that's a big deal.
Yeah.
So what we'll probably be seeing is we'll take infrared images and then we'll false color them so people can see these beautiful pictures that we've seen in the past.
Yes.
That's exactly the plan?
Yeah.
That's fantastic. Last question. What are you going to do on launch day?
I'll either be at the launch site to cheer, or I'll be back here to talk to the public. Don't know which one will be. There's such a limited number of people can go to the launch site that the people who really need to be there should be there.
Right. But are you, I mean, that's going to be a very anxious moment for you, I'm sure.
No.
No?
I don't get anxious about stuff I can't deal with.
Can you kind of tell me why?
Yeah. So I'm not anxious about things because I know that we're doing the right thing to make the best possible plan. So when somebody says we should worry about this, we worry about it and then we make a plan. So when you're 70 years old, you get tired of worrying about stuff. You just say, we'll make a plan.
I see. And you accept what happens.
Yeah.
That's interesting. That's interesting. And so I really like that. This is Dr. John Mather, and I cannot thank you enough. This is
Justin, a pleasure to talk with you, and look forward to seeing what you make.
I thought this conversation was fascinating on so many different levels. I came into it expecting to learn about science and astronomy and like how different things work, but I left with a sense of, it was just like a nugget of wisdom that Dr. Mather dropped on us there at the end. Think about it. This is one of the most complicated things that humans have ever done. There's a lot riding on this. There is a tremendous amount of investment of time, money, human lives, my family included. There's a lot riding on this. But when I asked him, well, aren't you worried? He said, no, because I've made the best possible plan. We've done our best. And then he just releases it. He's literally going to let it ride on a rocket. There's some deep wisdom there that I'm going to apply to my own life. If the man that's over one of the most difficult scientific endeavors that humans have ever done can make the best possible plan and then not worry and then like emotionally release that to say, we did our best, let's see what happens. If he can do that with this project, how can I apply that to my own life? Anyway, I thought that was amazing. I thought it was super deep wisdom, and perhaps that would be helpful for you as it is for me. This episode of Smarter Every Day is sponsored by KiwiCo, and what I like about KiwiCo is they send a kit to your house when you get a subscription, and it ignites the brain of a child that you love. One of the cool things about the James Webb Space Telescope is that it was created by a bunch of kids that grew up learning how to solve problems. So that's what KiwiCo does. These kits are awesome. Everything you need is included in the box. They teach really cool concepts in science, technology, engineering, arts, and math, and we love them. This particular one is a bottle rocket. I don't know how it's gonna launch yet. We're gonna figure out how this thing launches and have a lot of fun with it. What is that?
Citric acid,
Okay, what is this?
baking soda.
This particular one we're working on today is called a Tinker Crate, but there are 8 different subscription lines currently shipping to over 40 different countries. You can get your first box for free by going to kiwico.com/smarter.
Launch in 5, 4, 3, 2, 1.
I didn't land in the cup.
The thing I love most about the KiwiCo subscription is it encourages you to explore. Like, yeah, there's the experiment you do, but there's also all kinds of other ideas included in the kit, and you can do all kinds of things that are like coloring outside the lines, if that makes any sense.
Okay, this time let's try something else.
I love it. You will too. Go to kiwico.com/smarter if you want this for your family or a kid you love. I highly encourage it. In an upcoming video, we're going to learn more about the James Webb Space Telescope from my dad, who actually worked on the Sun Shield. very excited to share this with you. It was exciting for me to be able to go to see my dad do one of the coolest things that humans have done. I don't know, and it's my dad, right? I'm really excited about that. So I'll share that with you in an upcoming video, and I hope you enjoyed this interview with Dr. John Mather. I'm Destin, you're getting smarter every day. Have a good one. Bye.